Fields lecture 3 potential. Okay.
This is a new fire.
Is it what?
January.
Oh, that's just the last time I made changes to it. Yeah? Got that? Yep. Electric field potential. So, when a particle is above the ground, it has potential energy. Oh, that's because of forces acting on it, which could cause an acceleration, which could increase the speed, and therefore kinetic energy. And the kinetic energy must have come from somewhere, so it has potential energy at the start. So let me just explain that in a little picture here. This here will fall, obviously, and as it falls, it goes faster. And as it goes faster, it gets more kinetic energy. But that energy didn't come from nowhere, it had to come from another type of energy. So that type of energy it had at the beginning was potential energy. And the reason it had potential is because there was a force acting on it that was ready to accelerate it and give it kinetic energy. So in other words, if we have a force, then we have a potential energy. Because a force, like here, as I start, I'm given this kinetic energy. So the force is means there must be a potential energy as soon as the force appears. So like here, now it has potential, because if I let go, the force will bring it down, causing it to accelerate and gain kinetic energy. In other words, if you have a force, then you have a potential energy at the same time. And that's true for fields as well. So if you think about it, okay, so let's actually think about this in a lot of details. And this picture, if you want to draw this as well, it'll be helpful. So let's picture two situations here. So the first one, we'll go with the picture we know. So here is the Earth, the surface. Here is a particle here, and there's a force acting on it. And the force only really cares about its mass, because you can say F equals mg. So let me actually put the m in red here. G. Yeah? You also have the formula potential energy equals m g and h, and h being how far it is above the Earth. Okay, well, let's look at the picture now. Instead of this, let's imagine we're looking at something here that has a positive charge, and up here's another plate. Okay, now we'll call this plate negative. So what's going to happen here? There's going to be a force. What will this force equal? No, there's no gravity here. No gravity.
That is...
What force is this?
V over D. No,
yeah,
no.
Come on. What? EQ, yeah. And what is it, before I put in EQ, what is the thing about the charge that we care about for the force? We don't actually care about its mass, because will more mass make more force? No. Here more mass makes more force. Here, if I want more force, what do I need? More charge. So we care about the charge here. So you said this is EQ, didn't you? I'll just write that backwards for a moment. I'll just write QE, just so the Q's in front, okay? Now, if you were to look between the pictures, you'll see that they actually look pretty similar. Here you have a particle with some property called mass. Here you have a particle with some property called charge. Here you have something called, which is a force, which depends on its property mass. And here you have something which is a force that depends on its property charge. So if you were to actually guess what the formula might be for potential energy, by comparing the two pictures, you could probably have a good guess at it. What do you think it could be? Well, looking here and here, we think it should be a Q,
E,
an E,
H.
and a H as well, because we have the H here. It has a height. So, my point is, by drawing a comparison, we can actually get the formula potential energy is Q, E, and I use H, but I think in this formula, in the formula book, they might use D.
Could be then.
Yeah. So, just wait. There is a there is a difference though. There is a difference. This electric field strength, this E here, is a little bit different to the G. Because the G is a constant. Now the E, not really a constant. In fact, we have the formula for E. What is it? V over D. Now I'll just go back to calling this H for a moment. Now if I was to put that in, I would get QV over DH. Now just to be careful, what is the difference between H and D? The H is the height of the particle, and what was the D? The distance between the plates. So this is the D here. Now often, in fact 100% of examples I've seen in the exam, the particle always begins at the top plate, which means the D and the H are the same. So here I can cancel, and you end up with this very simple formula. The potential energy is just the charge multiplied by the voltage. Then that's all. So we've worked out potential energy is equal to QV. That is the formula here. Okay, now you can write this down, please.
Is it always QV or only if it starts?
Only if it starts at the top plate, which is actually 100% of examples I've seen in the exam. Okay, got that? Yeah, continue. So, you can say QV or QEH, depending on what letters they give you. So if they give you the Q and the V, then obviously just QV. But if you don't know the V, but you know the electric field strength and the distance between the plates, then you can go with QEH. I'm sorry, I keep switching between small q and big Q, and I haven't decided which I prefer. I'll have to figure it out one of these years. Anyways, you have the formula. Okay. Oh yeah, the cathode is, now you might know this from chemistry, the cathode is the name of the negative plate, and the positive plate is called the anode, yeah. Did you do these words in chemistry? No, you knew them from before? Yeah? Yeah. Continue? Yeah, okay. What are you doing in chemistry? Oh, yeah, okay. Now remember, well, actually, let's see if you remember. There's three things we can have. The potential energy can be positive, the potential energy could be zero, or the potential energy could actually be negative. So when the potential energy is more than zero, we say it has potential energy and it could do work and convert it into kinetic energy and all this type of stuff. What about if the potential energy is zero? What do we say?
Free.
It's free, very good. And if it's negative?
Trap.
It's trapped. Yeah. You see, it's good I did revision, because we said this in mechanics. Remember I drew the picture of the stick man, and he's falling, and he's in the hole? You remember my stick man? Yeah, and he's in the hole, he's trapped.
Oh.
Yeah.
I mean, I am in the below the ground.
You're trapped, so your potential energy is negative. Yeah. It's the same thing here with the fields. You could have a negative potential energy. In fact, when the electron is orbiting the proton, is it trapped or is it free? Well, it's trapped. Because when the electron is orbiting the proton, it's kind of stuck to it. It's trapped. And you know in chemistry what it's called to free an electron from a proton. Ionization. So ionization is actually sort of the cancelling of the negative potential energy by providing some energy. By ionizing, providing ionization energy. Okay, continue. Okay. So the conservation of energy implies that the initial energy the charged particle has must equal the final energy it has. So in fact that's, again, just revision of mechanics, nothing special here. But you can actually, we can actually make use of that here. So let's imagine I have two plates. Let me just draw them sideways. And what I'll do is I'll put a little hole in this plate and a little hole in this plate, okay? And we'll say that this plate's negative and this, what way do I'll put a small positive charge in it, and the field is going this way. And this plate is positive and this one is negative. So this one is the anode and this one is the cathode. When I put the small particle, I just gently push it through the hole, what will happen to it when it enters here?
Cool.
It will accelerate, and then it will shoot out here. Okay. Here it will have a kinetic energy, but that kinetic energy must equal the energy it has here. At the beginning, it's at rest, but it has a potential energy. So it means you could kind of say the QV, if you knew the voltage here and the charge of the particle, you could say that's equal to a half m v squared. So this is how you could work out how fast your particles hit the other side, what speed they're going at when they exit the field, when they finish accelerating. And I find this one is used quite a lot in the exam. It's fairly, actually I want you to write that down. It's actually a very common type of problem in the exam, is to calculate the V by using this formula. Yeah, so if you can make note of this situation, I'd say really common in the exam. Yeah?
But in the negative plane, the particle have still potential energy, right?
In which plane?
The negative plane. In negative plane.
Where?
When the particle too fast, then.
When it leaves here?
Yeah.
When it's out?
Yeah.
No. No more potential. All gone. Well, what force is acting on it?
No, this particle has potential energy. Only potential energy.
Yeah.
This goes this part.
Yeah.
And past this part.
Yeah.
And this only have kinetic energy.
Yeah. Yeah.
It makes sense.
Yeah, makes sense.
Why?
Why are you confused?
Does it make sense, right?
Doesn't it have potential energy as well, but just lower?
No. If it has potential energy, there must be some force that's causing the potential energy. So what force is acting on this? Like when it's left the field, there's no more opportunity for a force to accelerate it and give it kinetic energy. All the potential energy has become kinetic energy. It's the equivalent of when this hits the ground. You don't say it has any potential left in it. In this example, it's like it's hit the ground but has travelled through it, in a way.
This is potential energy.
Yes.
Boom.
Yes.
No kinetic energy. Boom.
Yes.
More kinetic energy.
Yeah.
And still potential energy.
Less potential. Yeah, but hang on. Now, positive,
Yeah.
negative,
Yeah.
positive.
Yeah.
So put it through here. Okay. Now stop. Right. At the moment it enters the field, it has potential energy.
Only potential energy.
Only potential. Well, basically no kinetic, because you gently pushed it
Yeah,
through.
yeah.
Okay, so let's start again. All right. No, slowly. No kinetic.
Okay.
All right. Okay. Lots of potential.
Yeah.
Go. More kinetic, less potential. Now, at this point, no more potential because it's leaving the field. The field is giving it potential energy. So it has kinetic. It's moving at a constant speed. Yes? See, it makes sense.
You should say it like that.
Well, it's a good thing I have you to help me. Thank you. Audrey, is that okay? The explanation was okay? Alright, continue. Now, we could, these are both energies, right? But you realise there's a kind of a small problem. Like, look at this. The voltage, is it a big or a small number? Well, usually it's not so big, not so small, like maybe 10 or 20 volts. But the Q, because we're talking about things like electrons and protons, the Q is usually big or small?
More.
Yeah, extremely small. So it's actually, we don't really want to use a unit like joules. In fact, we can't even really use a unit like nanojoules, because nanojoules is only -9, and this could be like -20. So we need a new unit to measure such small energies.
You can use the nanoscale.
Nano squared? No, not nano squared. Because the Q is so small, we use a different unit, and that unit is called the electron volt. And the electron volt is the energy gained when one electron is accelerated by 1 volt. Let me just, before you write that down, just draw that. So, if you have 2 plates, and the difference between them is 1 volt, and you stick in it a little electron, it will have potential energy, and it will accelerate up, and it will have kinetic energy, and of course these will be equal, and we call this energy that one electron gets when it's in 1 volt, we call that 1 electron volt. And if you think about the formula, what did I say it was? QV.
Yeah.
The energy potential energy equals QV. 1 electron volt will equal, well, what's the Q if it's 1 electron volt? That will be
1 point.
E, and V will be
1.
1. So basically 1 electron volt is E joules, basically. Now you can write the definition down. I just wanted you to have a picture in your mind. So first the definition here. If you like, you could draw the picture in a minute.
Potential minus 19.
So electron volt is like a unit.
Yep, exactly. Right, Jack.
It's a unit for Q.
For energy. Yeah. In the same way joules or calories are units for energy. Yeah? Yeah. Okay.
So EV is the unit for potential energy here.
No. You can still use joules because it's still energy. I'm just saying EV is a smaller unit of energy that is more appropriate to use because your numbers are so small. But in fact, you could, like, the energy I got from this drink you can measure in EV. It doesn't have to be this situation. It's suitable to use when you have any kind of small amount of energy to measure. Usually it's this situation, atomic, protons and neutrons, but it's just a unit for measuring energy, just like joules.
So we still write whatever, like to the power of minus 20 EV.
Oh no, you wouldn't. Like maybe I've got an example here. Yeah, so let's do an example. Convert 1 EV into joules. Okay, so 1 EV, 1 electron volt of energy is equal to 1.6 times 10 to the minus 19 joules. Yes? Oh, Sham, you're falling asleep. Starbuck night? What happened last night? You slept a lot. A lot.
That's the problem.
But I feel well that feels sleep, so.
Oh. Okay. Next one. Convert 1 joule into electron volts. So now 1 joule into electron volts. How can I do that? The opposite, yeah. So you just do 1 divided by E. So you can see that 6.24 electron volts. Oh, sorry, 6.24 times 10 to the 18 electron volts. So Audrey, can you see that if you have 1 electron volt, you actually have very little energy in joules. And if you have 1 joule, that's actually a lot of electron volts of energy. And the way you convert to go from electron volts into joules, you just multiply by E, and to go from joules to electron volts, you
Multiply by that.
divide by E. Yeah. Okay. Continue. Yep. So, two plates are 2 centimeters apart, and there's 500 volts between them. How fast will the electron hit the second plate if it leaves the first plate? So, what you've got here, plate, the distance is 2 centimeters, and it's 500 volts, and an electron starts here and fires across, and I want to know what's the speed here. Okay, I don't think this is too bad. Let's do it together. So what energy does the electron have here? Potential, yeah. And here? Kinetic. And they should be equal, of course. So that means QV should equal a half v squared. And I'm looking for the small v. So that means 2QV over m square root is the speed. Okay. What's electron, isn't it? What's the voltage? 500. Yeah. 13,262 kilometers per second. Yeah, isn't it? Q is the charge, so it's 1e is an electron. Now, do you notice what's interesting here? I actually didn't need to know that the plates were 2 centimeters apart. So I actually didn't use the 2 centimeters in my calculation. So it didn't actually matter. Yeah. I know it seems very fast, but the moment the electron hits anything like an air molecule, it will, come to rest nearly. Yeah. Okay. Yeah. Not too fast. Leave the electron alone. It's fine. All right. Continue. So I think I have one more example to do. Yeah. Now, an electron enters the field which is at 10 kilovolts, and the electron accelerates across the field until it hits 3 protons at rest on the positive plate. The electron binds to the protons and they move off together. The plates are some distance apart. How fast do they move off at? Right, so you've got your feet. Oh, it's great. I really like making good questions. Right, so you've got your plates here. No, I didn't say that. No. 10,000 volts. And what you've got here is proton, proton, proton. And here, electron. And the electron fires across, hits into this, and then they move off together.
With 3 protons.
With the 3 protons. They all move together. So the first thing I should work out, let me put a little hole here so they can be free. So the first thing I want to know is how fast the electron is going before it hits the protons. So I can say potential energy here equals kinetic energy here. Actually, it's just like the last question, isn't it? So I could probably even just be lazy and use the same formula I just worked out. 2qv over m square root. So v equals root 2qv over m. And in fact, I can just go back on my calculator and go back. What's the only difference here? The voltage, yeah, is now 10,000. So, woo, fast. Alright, shift, store A. So, what's that? That's 59,310 kilometers per second, which I have on my calculator as A. Okay. Well, that doesn't tell me how fast they move here, does it? That just tells me how fast the electron is going when it hits the 3 protons. But I want to know how fast do they move off together at. So what do I need to use now?
Conservation of momentum. Okay.
Yep. Conservation of momentum, because it's a collision now. So, M1, which is the mass of an electron, times U1, which I'm not going to write this number down, because it's on my calculator as A, I'll just call it A. So, M1 U1 plus M2, which is 3 protons, 0, equals MV, which the mass is ME plus 3MP, and we'll call it X. X here. So the X will be my answer I just got, times the electron mass, no plus, over mass of the electron plus 3 mass of the proton. Right, so let's see what we get here. Number 1, isn't it? Yeah. Oh, sorry, not answer. A. Okay. 10.765 kilometers per second.
Division question?
Stephen question.
Can you please go over this?
Yeah.
Why is the 593, the A, why is it kilometers per second?
Just because I like prefixes.
Did you fix the point?
Huh?
Did you fix the point?
I did, yeah. I didn't. I put in the original number in meters per second, yeah. The reason I do this is because it's hard to picture. Like if I said, I don't know, 600 meters per second, you're like, well, how fast is that? But if I said 59,000 kilometers per second, you know how big a kilometer is? 59,000 kilometers is what, like the circumference of the Earth or something. So you can kind of easily picture that this is going very fast. Isn't it like, I mean, here to America is, what, like 10,000 kilometers, is it?
America where?
Huh?
America where? Where's America?
Where's America?
Yeah. No, America is the big.
Okay,
Yeah.
East Coast.
East Coast.
Yeah.
Los Angeles.
No, Los Angeles is West Coast, isn't it?
No, East Coast.
Los Angeles is East Coast? Are you sure?
What do you mean? East Coast is just near the
Atlantic.
Yeah, that's the West Coast. In my opinion.
No, it's not an opinion, it's a fact.
In my view.
Yeah, okay.
Because I'm Korean.
Yeah, but when you describe a country's coast, it's as if you're in the center of the country. Not
when I see the center of a country,
yeah.
or
No, you
when
imagine you're looking at the center of the country. That's how you describe east and west coast.
Yeah.
Yeah.
That's right.
Yes, I understand. You're Korean, so yeah, it's at the center of the country. Okay, did you write this down? Yeah? Okay, so if you want some questions, and I think what we'll do is after 2 lessons we'll do a tutorial again on the 2 topics then, okay? I can close this?
Yeah.
Yep, alright. Do we have time to work on them?
Yeah.
And it's 5 minutes. So you can get a start for 5 minutes.